If we're going to be working with covalent compounds, it's going to be really helpful for us to be able to identify a covalent compound as well as figure out how to translate between a formula and a name. So first of all, identifying covalent compounds. The interactions between covalent molecules are typically weaker than the interactions between the ions of ionic compounds. So covalent compounds don't tend to have quite the same consistency when we're looking at their properties. So whereas ionic compounds were often crystalline and hard and brittle, covalent compounds can also be crystalline and hard and brittle, but they can also be very soft, and in fact they can be liquid or even gas. So they've got a much more varied set of properties. When we're looking at the elements involved in a covalent compound on the periodic table, covalent compounds tend to have elements that are closer together. So we said that an ionic has very far apart elements on the periodic table. Covalents, if the elements are closer together, they're more likely to form a covalent bond. And then finally, ionic compounds very often, not always, but we can usually recognize those pretty quickly because they've got a metal ion and a non-metal ion, either monatomic or polyatomic. Covalent compounds rarely have metals, at least the type that we use in this course, rarely have metals, and they usually have multiple non-metals in them. Now, a brief aside, there is a third type of bonding that I want to mention here. We're not going to spend a lot of time on this, but the third type is metallic bonding. If we're looking at things that are close together on the periodic table, again, we can't get closer together than the same element. So if something is a metal, how does that behave? Well, in a covalent compound, atoms share electrons in order to fulfill their outer shell. In a metal, well, that outer electron just isn't held very tightly, and it can jump around in the structure. This gives rise to a bunch of the properties of metals like conductivity, for example. So sometimes this is referred to as cations in a sea of electrons model, with the metal cations and a very loosely associated sea of electrons flowing around them. As I said, we're not going to focus on these a whole lot. I just wanted to mention them for completeness as we're talking about different types of bonding. What about naming those covalent compounds? Well, covalent compounds have much, much more variety in general than ionic compounds. So naming is, by necessity, has to be a little bit more complete and a little clearer in how we name it. So if we're talking about a binary covalent compound, a covalent compound that just has two types of atoms in it, we name them similarly to how we name organics. One of the big differences, though, is when we're looking at organics, we could use charge to predict relative numbers of different types of atoms. In covalent compounds, we don't have charge to work with. And a real quick and easy example is there's a very stable molecule that's CO. There's also a very stable molecule that's CO2. Well, we can't just call this carbon oxide because, well, these could both be called carbon oxide. How do we know which one we're working with? Well, that's where we use these numerative prefixes to tell us that this molecule specifically is carbon monoxide, mono, 1, versus carbon dioxide, di, 2 oxygens. So we're going to see these numerative prefixes used a lot more in covalent compounds. Now, a lot of covalent compounds were actually known long before the field of chemistry or even many of the sciences were developed. So because of that, there are a lot of common names that are floating around that we still use today. The most obvious one is water. H2O is water. Now, systematically, we would call this hydrogen oxide or dihydrogen oxide, but we don't call it that. We call it water because that's its common name. That's well understood in the field. A few other ones that we're going to run across pretty commonly are ammonia. Ammonia is NH3. It's a well-known molecule for a long time. Methane, principal component of natural gas, is CH4. And another one, acetic acid, CH3COOH. This is actually related to acetate ion, one of the polyatomic ions that's in your list to memorize. So we'll run into a few of these common names, but for the most part, we'll try to stick with systematic names because those are a little more general. So what do we do? What do we do when we're translating between names and formulas? These numerative prefixes are actually helpful to us because we don't necessarily, we don't have charge to help us, so we have to rely on the name. So sulfur dioxide, 2 oxygens. Dinitrogen monoxide, M2 dinitrogen monoxide, 1 oxygen. And it can be the first element, it can be the second element, it can be both elements. Diphosphorus pentoxide, P2O5. Again, the prefixes kind of write the name out for us. We also are going to continue working with formula masses. So just like with ionic compounds, we can add up the pieces to get the formula mass, the mass of the molecule we're working with. Now, when we're working with ionics, we use the term formula mass, and that was pretty straightforward. Once we move to molecules, once we move to covalent compounds, this is sometimes called molecular mass or molecular weight. But again, it's the same thing. Just add up the parts. Like in this diphosphorus pentoxide, we've got 2 phosphorus, we've got 5 oxygens. Add them up, and we get the formula mass of our diphosphorus pentoxide. So really, formula mass, molecular weight are all kind of interchangeable terms that are all referring to the same thing. Keep taking a look at different sources of names and compounds, and with a little bit of practice, these will start to snap in a lot more and make a lot more sense. See you next time.